Hey guys, welcome back to my channel. This is Dr. Rajeshwar from Pharma Tube. In the preceding video, we learnt the significant figures. If you did not watch the video, hit the I button on top right of this video to watch it. For the other topics of pharmaceutical analysis, click on the links given in the description below this video. In this class, we shall try to understand the theories of acid-base indicators. An indicator is a substance which is used to determine the end point in a titration. Acid-base indicators are also known as neutralization indicators. These indicators change color according to the hydrogen ion concentration of the solution. The chief characteristic of these indicators is that they change from a predominantly acid color to a predominantly alkaline color is not sudden and abrupt but takes place within a small interval of pH, usually about 2 pH units, which is termed the color change interval of the indicator. The position of the color change interval in the pH scale varies widely with different indicators. For most acid-base titrations, it is possible to select an indicator which exhibits a distinct color change at the pH close to that corresponding to the equivalence point. The equivalence point in the titration is the point where in the solution there is an equal molar concentration of titrant and analyte. In acid-base titrations, this is the point of neutralization. Acid-base indicators are weak organic acids and bases that have a dramatic color change in accordance with the solution's pH. Some of the indicators change in color, such as chlorophenol red, which is yellow at a pH of 4.8 and purple at a pH of 6.4. There are some indicators like phenolphthalein that at pH 8.2 is colorless and at pH 9.8 is either red or violet color. A simple representation of the ionization of an acid-base indicator is shown here. Since the indicator is a weak acid, at low concentration, the stronger analyte acid will titrate first. When the analyte has been neutralized by the titrant base, the weak indicator will react next and then change color. The figure given here lists a number of commonly used acid-base indicators with their pH transition ranges and associated colors. The transition range for the indicators is in approximately 2 pH units. Two theories have been proposed to explain the change of color of acid-base indicators with change in pH. Number 1, Ostwald's theory, and number 2, Quinonoid theory. Number 1, Ostwald's theory. Ostwald theory or Ostwald dilution law is a theory that describes that the behavior of a weak electrolyte follows the principles of mass action being extensively dissociated at infinite dilution. We can observe this characteristic of weak electrolytes experimentally through electrochemical determinations. This Ostwald theory was proposed by Wilhelm Ostwald in 1891. This theory is based on the Arrhenius theory. This theory states that the acid-base indicator is either a weak acid or a weak base that only partially ionizes in the solution. Therefore, there are ionized and unionized forms having different colors, which also means that the color change is due to the ionization of the acid-base indicator. Depending on the nature of the medium, either the ionized or the unionized form dominates the reaction medium, thus changing the nature of the medium can change the color of the medium. Normally, the unionized form has a different color than the ionized form. It is to understand that the ionization of the indicator is largely affected in acids and bases as it is either a weak acid or a weak base. In case the indicator is a weak acid, its ionization is very much low in acids due to common hydrogen ion concentration, while it is fairly ionized in alkalis. Similarly, if the indicator is a weak base, its ionization is large in acids and low in alkalis due to common hydroxide ions. Let's consider two important indicators, phenolphthalein, which is a weak acid, and methyl orange, which is a weak base, for explaining the Ostwald theory. Phenolphthalein, represented as HPH, being a weak acid, ionizes in solution to a small extent as shown in the equation. Phenolphthalein can change its color from colorless to pink when increasing the pH of the solution. The undissociated phenolphthalein is colorless while the phenolphthalein ions are pink in color. When phenolphthalein is added to the acidic solution, the dissociation of the phenolphthalein is practically nil or negligible due to increasing the concentration of the hydrogen ions, which means that the solution remains colorless. When strong alkali such as sodium hydroxide is added to the phenolphthalein, hydroxide ions furnished by alkali combine with hydrogen ions to form freely ionized water and sodium salt. The sodium salt of phenolphthalein remains in ionic state and imparts a pink color to it. The second example, methyl orange indicator, represented as MEOH, which is a very weak base and is ionized in solution as shown in the equation here. In the presence of an acid, hydroxide ions are removed in the form of water molecules and the equilibrium shifts to the right hand side. Thus, sufficient anions of methyl orange are produced which impart red color to the solution. On addition of alkali, the concentration of hydroxide ions increases in the solution and the equilibrium shifts to the left hand side, that is, the ionization of methyl orange is practically negligible. Thus, the solution acquires the color or unionized methyl orange molecules, that is yellow. The Ostwald's theory also explains the reason why phenolphthalein is not a suitable indicator for titrating a weak base against a strong acid. The hydroxide ions furnished by a weak base are not sufficient to shift the equilibrium towards right hand side considerably, that is pH is not reached to 8.3. Thus, the solution does not attain pink color. Similarly, it can be explained why methyl orange is not a suitable indicator for the titration of a weak acid with a strong base. And number 2, quinonoid theory. Quinonoid theory is a theory that simply describes how the color change of an acid-base indicator happens according to the changes in chemical structures. Here, we consider that an acid-base indicator exists in an equilibrium mixture of two tautomeric forms as shown in the figure. These two forms are named benzenoid form and quinonoid form. One of these forms occur in acidic solution while the other form occurs in the basic solution. These two forms also have two different colors that are helpful in showing the color change. During this color change, one tautomer form changes its structure to the structure of the other tautomer form. In other words, the color change is due to the interconversion of one tautomeric form into another. We consider the same examples of indicators phenolphthalein and methyl orange to understand the quinonoid theory. In the following illustration of phenolphthalein, the changes of which are characteristic of all phthalate indicators. See the formulas 1 to 4 given here. In the presence of dilute alkali, the lactone ring in structure 1 opens to yield structure 2 and the triphenyl carbonyl structure 2 undergoes loss of water to produce the resonating ion, that is structure 3, which is red in color. If a phenolphthalein is treated with excess of concentrated alcoholic alkali, the red color first produced appears owing to the formation of structure 4. Thus, the structure of phenolphthalein has two tautomeric forms, one is benzenoid and the other is quinonoid ring system. Similarly, methyl orange is also found in two tautomeric forms. Methyl orange has quinonoid form in acidic solution and benzenoid form in alkaline solution. The color of benzenoid form is yellow while that of quinonoid form is red. Therefore, the color of acidic solution of methyl orange is red and the color of alkaline solution is yellow or yellow-orange. Differences between Ostwald theory and quinonoid theory. Ostwald and quinonoid theory are very important in analytical chemistry regarding the acid-base titrations using indicators. The key difference between Ostwald theory and quinonoid theory is that Ostwald theory describes that the acid-base indicator is either a weak acid or a weak base that only partially ionize in the solution, whereas quinonoid theory describes that the acid-base indicator occurs in two tautomer forms that change from one form to the other to give a color change. This is the list of references followed for the lesson. That's all in this video, the theories of acid-base indicators. In the next lesson, we will discuss the classification of acid-base titrations. Till then, never stop learning and never stop watching my videos. Thank you for watching this video.